we present our work, multitasking across physical and virtual displays, the effect of spatial discontinuity and task load. Optical see-through head-mounted displays, like Microsoft HoloLens and Magic Leap, lets users access virtual information overlaid on top of the physical world. Virtual displays on OST HMDs supports flexible spatial arrangements, keep information accessible while you move around, and lets users quickly adjust the content, size, and even the presence of the displays on the fly. OST HMDs can be used for office work, supporting productivity, video or alerts monitoring, and collaboration on tasks like data analytics, as well as industrial work like assembly, maintenance, and construction guidance, and other areas like surgery and navigation. In some scenarios, users need to multitask across both virtual displays on an OST HMD and physical displays, creating a hybrid setup of displays. This can introduce challenges that are known to cause discomfort and performance cost. The first is having to shift attention between the physical and virtual environments, which is called context switching. Next, we have the focal plane switching. With an OST HMD, virtual content can appear at different depths, but the eye still focuses at one fixed distance. On a normal 2D monitor, the content is tied to the screen plane, so what you see and where you focus are usually aligned. This means that even if the virtual content and physical content appear to be at the same depth, the viewer may still need to refocus when switching between them. Such a hybrid setup is also a multi-display user interface, which can introduce spatial discontinuity between displays. You can have depth discontinuity, where displays are placed at different distance from the user, and visual field discontinuity, where displays are separated laterally in the visual field. We noticed that there has been little work exploring how these challenges play out in multitasking scenarios that require continuous monitoring and frequent switching between physical and virtual displays. In this study, therefore, we explored in this kind of scenario how hybrid display setup and spatial discontinuity between displays affect task performance and perceived workload. And since task load is often an important factor that can vary in real-world scenarios, we also looked at how task load modulates its effects. We recruited 20 participants, 10 females and 10 males. The study had 4 display configurations, and each one had 2 task load levels, for a total of 8 conditions per participant. I will first introduce the display configurations and then the tasks used in the study. The first display configuration is called desktop, where all 4 tasks are on a desktop monitor at 1.5 meters from the user. The second one is overlay, where 3 tasks are moved to the virtual display on an OST HMD, with the same appearance and control method, but 1 task still remains on the physical display. The physical and virtual displays are at the same distance from the user, but there is still context switching and a small focal plane switch of about 0.8 meters. In the third configuration, distant, the physical display is moved further away while the virtual display stays at the same distance from the user, creating depth discontinuity. And in the last configuration, misaligned, we add visual field discontinuity on top of depth discontinuity by shifting the physical display to the side, while still allowing users to switch between the 2 displays without moving their head. This image shows the study setup. We used a Magic Leap 2 OST HMD and a 27-inch monitor as the physical display. We also created a custom multitasking testbed with 4 independent tasks, inspired by NASA Multi-Attribute Task Battery, a widely used multitasking simulation. Task 1 is the shooting task, and it's always on the physical display. It's controlled with the 3-key mini keyboard. The left and right keys switch the cannon, and the middle key fires a laser at an incoming target before it reaches the end. There are also distractor targets that shouldn't be shot. This task creates a time pressure stream of events to induce interruption and encourage frequent cross-display switching. Task 2 is the system monitoring task, where the user responds to 3 types of event: bar rising above the line, the green button turning off, and the red button turning on, by clicking with the mouse. Task 3 is the tank monitoring task, where the user clicks one of the gauges when it moves into the red zone. Task 2 and 3 are continuous monitoring tasks with salient visual cues, representing parallel subsystem supervision. Task 4 is the perimeter entry task, where the user follows prompts to enter commands by clicking buttons. It's a discrete, multi-step task that requires focal attention and short-term retention, representing occasional control actions. We collected 3 measures: response time and number of errors for each task, and NASA task load index for perceived workload. Each condition had a 3-minute simulation with no primary task, meaning event frequencies were balanced across tasks. Events from the 3 tasks on the virtual display didn't overlap with each other, but they could overlap with the shooting task on the physical display. Task load was manipulated by changing the response window and the event frequency. We now move to the result. The plot shows the main effects of the display configuration for individual tasks, with the x-axis as the display condition and the y-axis as the dependent variable. Here is response time. We found that hybrid setup significantly increased response time in 2 of the 4 tasks. Compared to low task load, high task load decreased response time and made the differences between display conditions smaller, but all significant effects remained, except the difference between overlay and distant. The same 2 tasks, perimeter entry and shooting, showed significantly more errors in the hybrid display conditions. High task load further amplified these increases. Under low task load, there were no significant differences in the number of errors made. For perceived workload, all NASA task load index dimensions were adversely affected by 1 or more hybrid conditions, with no significant differences among the hybrid display conditions. The increases in frustration and physical demand were only significant under high task load. In summary, we found that multitasking performance declined and workload increased when tasks were distributed across hybrid displays that require context switching and focal plane switching, compared to using only a desktop display. Adding spatial discontinuity between displays generally did not worsen performance or increase perceived workload. We also found that task load amplified the number of errors and perceived workload differences between display conditions, but reduced response time differences, which may reflect humans' ability to tighten attentional focus under high time pressure. Performance reduction mainly showed up in the perimeter entry and shooting tasks, likely because these 2 tasks required more switching between displays. The limitations of this work include the small discontinuity range tested and the controlled multitasking testbed simulation. Future directions include testing more extreme discontinuity and broader multi-display configurations, using eye tracking to analyze visual attention, validating results in applied contexts, and exploring adaptive placement strategies for multitasking. Here we provide some key takeaways and design implications from the study. Designers of hybrid setups that combine physical and OST HMD virtual displays should minimize the need for frequent switching between displays. The good news is that small depth and visual field discontinuities between physical and virtual displays are acceptable in terms of performance and workload. Designers should consider task characteristics, such as how often a task requires users to switch to other displays, and how time-sensitive it is. And finally, designers should be prepared for the effects of task load on both performance and perceived workload. Please refer to our paper for more details on the study and the result. Thank you for your attention.